Hello everyone, my name is Gregor Fasching and together with Stefan Radl I will guide you through the discrete element method MOOC. To give you a little insight into what you will learn in this course, I would like to hand over to Stefan.
Welcome to this first unit. Let me start with what you will learn in this unit. We will start with an overview of different simulation methods. Then I would like to show you a typical particle simulation that uses the discrete element method. Also, I will highlight the industrial impact the DEM had already. At the very end of this part, I will hand over the voice to experts. I will ask them about their opinion related to the DEM. But now let's start with an overview of the different methods. The first big group of methods are the so-called Eulerian methods. Here, discrete physical entities, for example particles, atoms, molecules, are smeared over a control volumina. These control volumina are often called representative volume elements, or in short RVEs. For each of these RVEs, balance equations for properties can be formulated. For example, for the fluid velocity u or the pressure in the RVE. X and t here indicate that these properties are a function of space and time. It is important to note that RVEs are spatially fixed. Only a relatively slow motion or small deformation of RVEs is typically allowed. Eulerian methods are typically called computational fluid dynamics, or CFD, the finite volume method, or the finite element method. In contrast to Eulerian methods, there is the big group of Lagrangian methods. Here, discrete entities are tracked in space and time. For example, we are interested in predicting what is the change of the particle's position xp and the particle's velocity vp over a finite time step delta t. Lagrangian methods track particles, atoms, or fluid elements. If we do the latter, we typically call the particles parcels. They are also called mesh-free methods because the moving particles are essentially the computational mesh to evaluate the physical properties. The discrete element method or the smoothed particle hydrodynamics method are prime examples of this group of methods. In order to further contrast the different methods, I would like to introduce to you the so-called continuum. Continuum is very often used interchangeably to an Eulerian method. When we follow such a continuum approach, we need to use constitutive laws to relate the stress in the material and the strain, for example. If we are interested in fluid flow, we very often also consider the strain rate. In contrast to that, there are the so-called discrete or Lagrangian methods where we track individual particles. Here, particle interactions are important since they govern the motion of the particles. So we are interested in the force versus displacement or the force versus overlap behavior of the particles. We will spend enough time in the later units to discuss what we mean here in detail. So now let us zoom into the Lagrangian methods. Here we can also distinguish different types. The first type of Lagrangian methods is the one that tracks particles. Also droplets or bubbles can be tracked, as they are essentially fluid particles. Here we can distinguish between Lagrangian methods that consider realistic interactions between the particles. Here the DEM fits in. Also the so-called coarse-grained DEM fits into this type of Lagrangian methods. Please don't worry too much about all these abbreviations. In the separate document on the nomenclature and abbreviations, you'll find all the details related to this. The second big subtype of Lagrangian methods for particles is the method where we track no interaction between the particles or only very simplified interactions. These methods are typically called particle tracking methods. The third type are so-called statistical tracking methods, of which the multi-phase particle in cell method is a prime example. The second big type of Lagrangian methods is used for modeling of fluid flow. A fluid can be a gas, a plasma, a liquid, a soft solid or a paste, for example. The first important subtype of these methods is the so-called smoothed particle hydrodynamics method. Here we smooth or average over surrounding discrete elements to calculate the fluid motion. A second subtype are bonded particle methods. Here we have simply bonds between the parcels that make up the fluid. And a third approach would be to use a so-called statistical tracking of the interactions, where we then speak of a so-called dissipative particle dynamics, a direct simulation Monte Carlo, or a particle in cell method. Last but not least, there is the important group of mesh hybrid methods for fluids. The particle finite element method and the lattice Boltzmann method are examples for this subtype of Lagrangian methods. At the very end, we can highlight here Lagrangian methods that track individual atoms. If we track them in a deterministic way, we speak of a so-called molecular dynamics or a coarse-grained molecular dynamics code. If we perform a statistical tracking of atoms, then we would speak of a kinetic Monte Carlo method, for example. As you already see, there is a huge variety of Lagrangian methods, and they had a huge impact on our daily life in research. Let us now continue with the definition of the discrete element method. The DEM is a Lagrangian numerical simulation method to describe particles or fluid particles, and those fluid particles we typically call droplets or bubbles. I hope you have enjoyed this very first part of this MOOC. See you in the next unit.